All right, we're going to finish up chapter 22 and then we will review. All right. All right, we're going to do some valence bond theory. We're going to look at our complex here. And this is a hexaamine chromium 3 complex. And we're going to do ligand electron counts. And we're going to get the d electron count. And we're going to get the total electron count. So when we were naming our compounds, if we go back to the naming part, just for a quick review, if you have a negative ligand, a ligand that has a negative charge, the ligand name ends in O. All right, so as a ligand, bromine is bromo. As a ligand, chloride is chloro. Cyanide is cyano. All right, and so anytime we have a ligand name that ends in O, or if we do the Lewis structure, the reason why it's negative is that your bromine has to have an octet. And when it has an octet, it has 8 electrons and it is a negative charge. All right, and every time you connect to a metal, it is a coordinate covalent bond. That's 2 electrons go to the metal. And so we're going to count bromo ligand as a 2 electron minus 1. Same as chloro. Same as cyano. Same as fluoro. Same as hydroxo. All right, and those are the ones that we're going to see on our electron counting. All right, so they will all be 2 electrons and minus 1. When we have our neutral ligands, ammonia is neutral because when we draw the Lewis structure, it has an octet and it does not have a charge. Nitrogen, 3 bonds, electron pair, that's what it's supposed to be. And so that is a 2 electron and no charge. It's neutral. Same as CO. When we draw the Lewis structure of CO, it is interesting because carbon should not have 3 bonds and electron pair. That carbon is negative. Oxygen should not have 3 bonds and electron pair. That oxygen is positive. And so you have a negative and a positive, and the net charge is 0. All right, and so it connects to the metal through the carbon. All right, and so it is a 2 electron. It is 0 because it has both a negative and a positive charge on CO. And then water, all right, again, water has 2 lone pairs. One of those lone pairs will connect to a metal, and it is a 2 electron neutral ligand. All right, now the difficult one is ethylene diamine. All right, they're going to write En. And so you need to know ethylene diamine is NH2, CH2, CH2, NH2. So one ethylene diamine will have 2 coordinate covalent bonds to the metal. And so one ethylene diamine is a 4 electron neutral. And so both of those nitrogens have 3 bonds and electron pair. They are neutral. But one ethylene diamine has 2 connections, 2 coordinate covalent bonds, and so it is a 4 electron neutral. All right, so when we go back to our structure, well, let's do these here. If we want to do the electron counts for these structures, all right, we have the first one is a platinum, and then you have your NH3 sub 4, and then you have Cl2. that's your ligands. Remember that if you are outside the bracket, whether it's after or if it's before, it is not a ligand. All right, and so this one has a coordination number of 6. 4 NH3s, 2 Cls, and so anytime you have a coordination number of 6, you are octahedral. All right, and so now we know that the NH3s are neutral, and so you have 4 of them, so that's 8 electrons with a 0 charge. All right, because we just did NH3 was 2, 0. Cl is a 2 minus 1. If you have 2 of them, then you have a 4 electron minus 2, because you have 2 of them. All right, and so this, when we took off the Cl2, the 2 Cl minuses, that is a plus 2 here, and you have your 2 Cl minuses, and you would have an I value equal to 3. All right, so when you take that and you don't bring these other 2 chlorines, this is a plus 2 charge. And so your platinum is 4. So you have a platinum that is plus 4, you have a 0, you have a minus 2, you have an overall of a plus 2 charge. All right, so then after we have our oxidation of our metal, we want the d electron count. The d electron count are the S and D electrons past the noble gas core. All right, so if we find platinum on the periodic table, and it is number 78. All right, so this is a review for the final. If we're doing a electron configuration for just platinum, then we'll do platinum plus 4. Both of those we've done before. You have the first prior noble gas, which is Xe, which is 54. That takes up 54 of our electrons. Then we go to 55. All right, and so that starts to 1, 2, 3, 4, 5, 6 S2. All right, then you go to 56 and then down to 57, which is the lanthanide series. So that's the 4F. You fill that up until you get to 103 or 71, which is the 3, 4, 5D1. So that's 5D. Except we have to go out to platinum, which is you count over 8 spots before you get it. All right, if you want to add those up, 54 plus 2 is 56, plus 14 is 70, plus 8 is the 78 electrons. If we had a platinum 0, and I asked for the d electron count, the d electron count for a neutral platinum would be the s electrons plus the d electrons. We add the s electrons to the d electrons, and this would be a d10. We would not put a 5 in front. We would not put any number in front. The d electron count is just called d10. This is platinum 4. So if we go to platinum 4, now we're doing plus 4. That means we have to get rid of 4 electrons. Now, when they write this answer in the book, they write 4F14, 5D8, 6S2. They do that because when you get rid of them, you get rid of the highest energy electrons first. That's the 6S2. Then the next highest would be the 5D8, and that would come down to a 6. And so that would be Xe, and then 4F14, and then a 5D6 for platinum plus 4, which means it lost 4 electrons. So instead of D10, it is D6. All right, and so platinum 4 is D6. Now, the easy way to get it, when you have your periodic table, you look at the number right above the column of platinum is a 10. That means that neutral platinum is D10. And then you have plus 4, so you have to remove 4 of them, and that is D6. So there is a number above all of your transition elements. That for platinum is a 10, so that's where you're going to start. If it's plus 4, you take off 4. It's D6. All right, so then we get our total electrons. That means we add the d electrons plus the ligand electrons. So our d electrons, we have D6. plus the ligand electrons, we have 8 for the 4 NH3s, and we have 4 for the 2 Cls. And that gives us 18 electrons. All right, and that's sort of like the octet in Lewis structures. When you're doing a coordination compound and you get the number 18, the chances of that being stable are excellent. That is a very stable, it's the most stable number of electrons. All right, so we have two numbers that are going to be stable. Almost every complex that has 16 electrons or 18 electrons, those are going to be very stable. All right, so we're going to get a lot of 16 and a lot of 18 electron complexes because those are the most stable. You can have any number of electrons, and sometimes they're stable and sometimes they're not. 16, 18, usually the stable electron counts. All right, so let's go back to where we were before and look at our valence bond theory. All right, so we can do the electron count of our chromium here. So now we know that we have 6 NH3s, so our ligand electrons is a 12, 0. So we have 12 electrons and a 0 charge because we have 6, 2 electrons. It is neutral, and so the chromium is +3. Chromium is +3. So you can do the electron configuration of chromium, take off the 3 electrons. For our D electron count, all we have to do is find chromium on our periodic table, which is number 24. Look at the number above it, which is a 6, and know that we're looking at a chromium that is a D3. So a chromium plus 3 is D3. The number above chromium is a 6. All right, and so when you have neutral chromium, it is D6. When you have chromium that's +3, then you have D3. All right, plus the 12 electrons will give us our 15 electron complex. All right, we would not predict a 15 electron complex to be stable. This one is a stable complex. The only ones we predict to be stable are the ones that are 16 or 18, but other ones are stable, and this one is a stable complex. All right. And this is a coordination number of 6. The coordination number is 6 because there are 6 ligands attached to the chromium, and therefore it is octahedral. If you have a coordination number of 6, you are octahedral. All right, so your chromium +3, if you did the actual electron configuration, you would take first your chromium, which is argon, and then 4s2, 3d4, except we remember that chromium is one of our exceptions, and so it's actually argon, 4s1, 3d5, so all of the electrons in there are half full. That is not going to affect us at all in getting the d electron count, because the d electron count is the s and the d electrons past the noble gas core. If you write it this way, it's 6. If you write it this way, it's 6. Either way, your chromium neutral is a d6. So chromium neutral is d6. Now we want chromium +3. So we're going to take off 3 electrons. So we take off the highest energy electron first, the 4s1, and then we take 2 of these, and we end up with argon 3d3. All right, so when you have octahedral, and you have octahedral because your coordination number is 6, you're going to have your 5 orbitals. These are your d orbitals. When you are octahedral, 3 orbitals are more stable and 2 are less stable. All right, so due to the bonds coming in and their orientation. All right, and so you're going to have 3 on the bottom, 2 on top. When you have D3, you stick in the 3 electrons, 1, 2, and 3. All right, So your hybridization for octahedral is either going to be sp3d2 or d2sp3. If these are empty, then you have d2sp3. These have to be completely empty. Both of them have to be empty. So if empty, which it is for this D3, the hybridization for this is a D2sp3. If there was one or more electron in either one of these two orbitals, it would be sp3d2. If they are empty, then you fill those first. Those are the two Ds. Then you go to S, then you go to P. If they're occupied, then we go to the S and then the P and then the D at higher energy levels. All right. So that is the crystal field theory. That's when you break it into 3 on bottom, 2 on top. So we are going to study the octahedral, 3 on bottom, 2 on top. The tetrahedral, which is reverse of the octahedral, which has 2 on bottom and 3 on top. And then the square planar, which is 2, then 1, then 1, then 1, orbital. All right. So when we put in our, you have your X, Y, and Z axes. When you do a octahedral, you have the electrons coming in here, and here, and here. So that is your octahedral. So that is showing your octahedral. All right. So the reason why this is a higher energy, and you don't really need to know this, but I'm going to tell you, and this is why, is you have an electron pair coming in where there is a negative charge. And so you have a negative with an electron pair. It's going to repel. It's going to be at higher energy. Same thing over here. You got your ligands that are coming in. You got your negative charge. And so you're going to have repulsions there. It's going to have higher energy. Over here, we don't directly have an orbital on any of these negative charges. And so those are more stable, lower in energy. We don't need to know that, but that is why you're going to have 3 at lower energy, 2 at higher energy. That's what you have to know. And the distance between them is called delta. So you don't need to know the dz squared, the dx squared minus y squared, the dxy, the dxz, and the dyz. You just have to know that 3 of them are lower energy, 2 of them are higher energy. I will not ask for the specific orbitals. All right, and so, but we will need to know that the distance between the higher and the lower is called delta. That is simply an energy. All right, now when we have octahedral, we're going to talk about high spin and low spin. So octahedral can have high spin or it can have low spin, and you have to be able to predict which one would be a high spin, which one would be a low spin. All right, now a high spin, and what it means is if we have our orbitals, and our orbitals look, say, like this, versus our orbitals over here that look like this. All right, so what I'm showing is that your delta is the difference between the higher and the lower. Your delta is the difference between the higher and the lower. So if you have a large delta, a large separation between the higher and the lower, then the electrons are going to pair up and stay at the bottom. So let's take a D6. We're going to look at a D6. What if it were high spin? Now, high spin means you have your first 3 electrons go in the same way. The first 3 electrons will go in the same way. It doesn't matter if it's high spin or low spin. If we are high spin, that means our delta is very small, and so we will go up that amount of energy, and we will go up here and up here for 5 and 4 and 5, and then 6 we come back down to the beginning. Over here is low spin. That means your delta is very high. It's a very high energy to go up to that high energy orbital. It is lower energy to pair it, and so we pair the electrons, and so we pair it. We pair the electrons. And so a D6 low spin is diamagnetic. It has 0 unpaired electrons. And this one is paramagnetic because it has 4 unpaired electrons. All right. So you have a difference, high spin, low spin. And so it's all about the delta. And so if your pairing energy is greater than delta, that means your delta is small. Pairing energy doesn't change. That's the same amount of energy for your electrons. It is the delta that's going to change. All right. So if your delta is very small, which means your 3 over your 2 are very close together, then you're going to have a high spin. All right. So if your pairing energy is less than your delta, so your delta is a big number compared to the pairing energy. All right, it's going to do what's lower in energy, and this is your low spin. So that's where your pairing energy is lower than the delta. So it is less energy to pair than it is to go up, and so it pairs up. It's going to do whatever is lowest in energy. And the reason why we have a high spin versus a low spin is all based on the ligands. So high spin, all ligands are weak field. If you have one or more strong field ligand, you're going to be low spin. So low spin is when you have one or more strong field ligand. All right, now the weak field ligands, these are your halogens and oxygen. So halogen, whether it's a fluorine, chlorine, bromine, iodine, any halogen that's attached is a weak field ligand. If you have an oxygen attached in the OH or your H2O, those are weak field ligands. The strong field ligands are going to be your nitrogens. If you are connected through a nitrogen, that is a strong field ligand, NH3, ethylene diamine. All right, and then the other one, and then of course CN, so the kind that will bind and never let go. Your CN minus is a very strong field ligand, as well as carbon monoxide. So CO, very strong field ligand. All right, so here is the list of your ligands. All right, so your weak field or weak bonding ligands, I call it field, weak bonding or weak field ligands. I call that field. All right, so you've got your halogens, and then you have your OH and your H2O. Your strong field or strong bonding ligands, I call it field. All right, is your NH3, ethylene diamine is 2 NH2s, one on each side. You got your NO2 minus connected through the nitrogen, the nitro group, and then you got your CN minus. When you do your Lewis structure for CN minus, there you see your negative on your C, but your neutral nitrogen. That's why it is CN minus versus the CO, which also has the triple bond and the electron pair and the negative carbon, except for this oxygen with 3 bonds and electron pair is positive, and so that is a neutral ligand for CO. All right, so you need to know your weak field ligands, these weak field ligands, and you need to know these strong field ligands. If you have a strong field ligand, you're going to have low spin. If all the ligands are weak field ligands, then you're going to have high spin. Remember, it only requires one strong field ligand to be low spin. Be high spin, all of the ligands have to be a weak field ligand. All right, so let's do this problem. We're going to do electron count. So we have Fe H2O sub 6 plus 2. So we're going to do our Oxidation of iron. Well, we know water is neutral. And so we know that water is a 2-electron neutral, but we have 6 of them. So that's 12 electrons and no charge. So the iron has to be plus 2 because the overall charge is plus 2. So then we go to our periodic table, we find iron, number 26. We look at the number above the iron. It is an 8. So we know that iron 2 is D6. Because on the periodic table, iron 0, right on the periodic table, the number above it is 8. So an iron 0 would be D8. This is iron plus 2. It is D6. Plus the 12 electrons from the water ligands, and we got an 18-electron complex. And that is going to be predicted and is a stable compound. All right, and we know that it's octahedral because our coordination number is 6. When your coordination number is equal to 6, you are octahedral. All right, now we have water. Water is a weak field ligand. H2O, weak field ligand. And so now we know that it's going to be a high spin. All right, and so when we draw our orbitals, let's draw them this way. We're going to draw them with lines. All right, and I'm going to keep the 3 and the 2 pretty close together because it is high spin and I know my delta is low. All right, so you put in your 6 electrons. The first 3 go in the same no matter what spin it is. Now we have weak field ligands, we have a high spin, and so we go and we spin our electrons in the higher energy orbitals. And then we need one more. That comes back down to where we started. And so there is your high spin D6, which has 4 unpaired electrons. And it is paramagnetic, which is attracted to a magnetic field. All right, if we do the other one, FeCN sub 6 minus 4. Again, we have a 6. That means it's octahedral. Coordination number is 6. It is octahedral. Oh, over here. We skipped that part. The hybridization. Since we have 1 or more electron in these higher energy orbitals, this is an sp3 D2. In order for it to be D2 sp3, the 2 on top would have to be empty. All right, so coordination number is 6. It's octahedral. We do the electron count. So Cn, we just did it. Cn has a negative charge. And so it is a 2 electron minus 1, as we in the name, cyano, hexacyano iron. And now we have to find the oxidation of iron. So this is minus 6. To get a minus 4, we have to have a plus 2. So it's iron 2. So hexacyano iron 2. This is hexa-aqua iron 2. That's the name. All right, and so now we have iron 2, which is again the same as over there, iron 2, which is D6, because iron 0 on the periodic table has the 8 above it. So iron 2, lost 2 electrons, D6. All right, so you got your iron 2 D6 plus the 12 electrons for your 6 Cn minuses. All right, so you have 1 Cn minus is 2 minus 1. 6 of them is 12 electrons and a minus 6. And so the electron count, the ligand electron count is 12 electrons. And so our total is 18 electrons predicted and is a stable complex. All right, and so now we have to look at the ligands. We have Cn minus. Cn minus is a strong field ligand. All right, that means it's going to be a low spin. So now when we write our 5 orbitals, 3 on the bottom and 2 on the top, I'm going to spread it out a little more because I know with strong field ligands, you're going to have a larger separation in your delta. And so when you put in your 6 electrons, The fourth one is not going to go up high spin. It's going to stay down low and spin. And so you now have a diamagnetic, 0 unpaired electrons. So you're diamagnetic, 0 unpaired. All right. And now when you do the hybridization, since those two on top are empty, now it is a D2sp3. All right. So when you're octahedral, it's either going to be sp3d2 or D2sp3. In order for it to be D2sp3, these two orbitals have to be empty. All right, so now they switch it to cobalt. All right, so we have a cobalt. So we have a hexa aqua cobalt 2. All right, so you find cobalt on your periodic table. The number above your cobalt is 9. So on the periodic table, I looked at cobalt. Cobalt 0 would be a D9. All right, but this is cobalt plus 2. So now we have cobalt plus 2, which is a D7. All right, we have 6 is our coordination number. Right here, we have 6 H2Os. So the coordination number is equal to 6. We know that we are octahedral. All right, so now we get our ligand electron count. So 6 waters, that's going to be 12 electrons and neutral. So when we add our D7 to our 12 electrons, we get a 19 electron complex. All right, and so your cobalt complex with water would not be predicted to be stable because it's not 16 or 18, but this is a stable complex. All right, we only predict the 16s and 18s to be stable. The other ones may or may not be stable. You would have to make them and see. And this one is stable. But again, 19 electron complexes, most 19 electron complexes would not be stable. This one is stable. All right, and so now we have our ligands, and we have weak field ligands, H2O. That is a weak field ligand. All right, and so it's going to be high spin. And so when we put our 3 orbitals on bottom and our 2 orbitals on top, and they're going to be relatively close together because they're high spin. All right, so then 4 and 5, high spin, are going to go up there. And then 6 and 7, we go back down and pair up. So we have 3 unpaired electrons. And it's paramagnetic. All right, so now, since there's electrons in this d orbital, the hybridization is sp3d2. In order for it to be d2sp3, those 2 on top would have to both be empty. All right, so if we change it to a CO, and then we did the same thing that they did last time, and now we're going to use CN, and we're going to use 6 of those, and now it's going to be a -4. So this is -6, this is +2 to give an overall of -4. So it's the same, except we changed the ligand from a weak field ligand of water to a strong field ligand, that is Cn-. So we are still cobalt 2, we are still D7, we are still plus 12, 19 electrons. And now we have our octahedral splitting pattern, except our Cn is strong field, and we're going to have a low spin complex. So now when we put in our 7, 1, 2, 3, it is low spin, 4, 5, 6, and 7. We have one unpaired electron, and so it is paramagnetic. All right, and since we have one electron in the higher energy orbitals, then we have to go to sp3d2. Again, the only way to get T2 sp3 is they both have to be empty. And then this one is got an error. When we did the high spin, it's D7. And for the high spin, the 7 is there. The low spin is correct. All right, and then your high spin has 3 unpaired electrons. Your low spin for D7 would have 1 unpaired electron. All right, so high spin and low spin would have the same number of unpaired electrons. So it would be the same if you have D1 through D3. So you put in 1 electron the same, 2 electrons the same. The first 3 electrons are put in exactly the same, no matter what the D electron, whether it's high spin or low spin. All right, and once you get past 7, 7's different, but if you had D8, 9, or 10, also would be the same. All right, actually, you can put a 0 there. So if you had no electrons in there, well, they would be the same. They'd both be empty. 1 would have 1 in the first 1. 2 would have 1 in the first 2. 3 would have 1 in the first 3. All right, then 4 would be different, and 5, 6, and 7 would be different. Now, when we get to 8 and we're high spin, now we would put that electron in. And then here, we would put the next electron right here. So a D8 and a D8, whether it is high spin or low spin, would have the exact same configuration of 2 unpaired electrons. D9 would have the exact same configuration of 1 unpaired electron. And in D10, both would have completely full orbitals. All right, so the only difference that we're getting for high spin and low spin is between D4 to D7. Those are the ones that are different. 0 through 3, 8 through 10, they would be the exact same configuration, regardless of high spin or low spin. All right, now we're going to do coordination numbers of 4. If your coordination number is 4, then you're going to be tetrahedral or you're going to be square planar. If your coordination number is 6, you're always going to be octahedral. When it's 4, you can be tetrahedral or you could be square planar. If we are predicting, we are only going to predict square planars to be D8. So if your coordination number is equal to 4 and you are a D8 metal, then we are going to predict square planar. Any other coordination number of 4, and it is D not equal to 8, then it is going to be a tetrahedral. So this again is just a prediction. All right, there are square planars that aren't D8, and there are tetrahedrals that are D8. But in general, you're going to get it right 90% of the time if you're predicting your D8 coordination number of 4 to be square planar. But 10% of the time, it would be tetrahedral. So they do exist as tetrahedral or square planar. But again, a high percentage of coordination number 4, D8, are square planar. So that's why we would predict that to be a square planar. All right, now we don't have to worry about high spin or low spin because tetrahedral is always high spin. And square planar is always low spin. It makes no difference what the ligands are. If you're square planar, you're low spin, period. If you are tetrahedral, you're high spin, period. No exceptions to that. All right, because the delta for your tetrahedral is very small, half of that of your octahedral field. So they're all high spin, doesn't matter what the ligands are. And in your square planar, your delta is very large, and it is always a low spin for square planar. All right, so here are the 5 orbitals. Now for your tetrahedral, we simply inverted our octahedral. Now we have 2 on the bottom, 3 on top. All right, so this is your tetrahedral. And this is your square planar. All right, so 90+% of the time, your square planar is D8. All right, and so you're going to have your, well, you got your first 4, and then you put your next 2, and then you put your next 2. All right, so here's your D8, and that is your square planar D8 that you're going to see about every time you do a square planar. Now, these two orbitals are very close in energy, and many books put them at the same energy level. And so if you see any examples where the square planar looks like this, all right, they're saying that these two orbitals here are such similar in energy, the energy difference is very small. Some will separate them, and some will leave them the same. Regardless, you do your D8, and it doesn't matter because the electrons are paired in both of those d orbitals. Now, the top for square planar is always empty. So since this is always empty, the hybridization for your square planar is d sp2. Again, your coordination number is 4, so you only need 4 orbitals. Since that d orbital is empty, we use it, then we use an s, and then we use 2 p's. Your tetrahedral is the usual sp3. All right, so a tetrahedral is always sp3 hybridized, and your square planar is always d sp2 hybridized. Again, your tetrahedral is always a high spin, and your square planar is always a low spin. So if it asks if it's high spin or low spin, do not look at the ligands. Square planar, always low spin. Tetrahedral, always high spin. If I have 4 cyanides on this tetrahedral, it's still high spin. It doesn't matter that cyanide is a strong field ligand. If I have 3 bromines over here, it doesn't matter that you have weak field ligands. It's always going to be low spin if you have square planar. It's always high spin if you have tetrahedral. All right, these complexes are very colorful, and they are colorful because they absorb in the visible region of the spectrum. And what's happening is the d electrons are moving from the higher energy to the lower energy, and then that energy is being emitted, and that is in the, again, the visible region of your electromagnetic spectrum that we can see. All right, now if there is no color, white or colorless, that means that you don't have any D to D transitions. That means that you have a D0 or you have a D10. All right, if you are D0, you don't have any electrons to move from higher to lower. If you are D10, they're all full and they can't move. All right, so you have to have some number of D electrons between 0 and 10. And to calculate that energy, your energy is equal to h nu. Remember, h is Planck's constant, 6.626 times 10 to the minus 34 joules times seconds. C is your speed of light, 2.998 times 10 to the 8th meters per second. Your nu, this is nu, that is not V, that is nu, that is your frequency. And that is in 1 over seconds or hertz. Hertz is 1 over seconds. And then lambda is your wavelength right here on top, the wavelength lambda. All right, so that is in meters. So lambda is your wavelength. And that's going to be in meters for the units of your wavelength. All right, when we do our visible region, we are going to put the wavelength in nanometers. So nanometers is equal to 1 times 10 to the minus 9 meters. All right, so when we're doing nanometers, which is visible light, they usually put it in nanometers, like they have here. Your wavelength is in nanometers. All right, so we just saw it. We have E is equal to hc over lambda, the wavelength. All right, so the larger your wavelength, the larger the wavelength, the bigger number you're dividing by, the smaller the energy. And so this is the lowest energy, and this is the highest energy. And we have our electromagnetic spectrum. The way I like to do it is from low to high energy. All right, so you got your radio waves, you got your microwaves, you got your infrared. Then you have visible. And then you have ultraviolet. Then you have X-rays. And then you have your gamma rays. All right, invisible. I left a little spot here because notice that your infrared in the visible, it is red, orange, yellow, green, blue, indigo, violet, ultraviolet. So it's Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. All right, so the lowest energy is red. So the lowest energy is red. The highest energy is violet. The highest energy is, well, they call it blue, but violet. All right, and so here is your spectrum. Now, when you have this, the highest spot here, that's called your lambda max. And we have, all right, so again, to get your color, what's happening is your electron transfers up to a higher energy, and then it goes back down and emits energy in the form of visible light. And that's why you have very colorful transition element complexes. All right, and so here is your absorbed color versus your observed color. So right here is the color that we see. This is the color observed. So here is the color that is absorbed. All right, and so here is our red, orange, yellow, green, blue, and indigo violet. All right, and so this is, of course, the highest wavelength. All right, so 680 for the red. All right, and so this is the lowest energy. And this is the shortest wavelength, and that is the highest energy. All right, and so when you have a compound that is yellow, and you see yellow, that means that the color absorbed was in the violet to blue region. And this doesn't work perfect, but I like to use it. It is a good estimation. My color wheel. All right, and so I just put in my red, orange, yellow, green, blue, and then I put indigo and violet in the same one. All right, so I know if I see red, I know that that absorbed green. So if I see red, that's what I see. I see red, I know it absorbed green. Well, blue, green, green, okay. So it gets you in the correct ballpark. If I see yellow, I know that it absorbed in the indigo and violet. So if I see yellow, it's violet blue. Okay, so I like to do my little color wheel, and then I know that the one 180 degrees away from that color, that's the color that was absorbed. I know the color I can see, I'm looking at it. What color was absorbed? That is from the color wheel. All right, so that is the end of chapter 22. So now we're going to work some problems out of chapter 22. Oh, first I want to go back to the, let's go, I want to finish that one section. All right, so we did, it's been erased, so we'll redo it. We were here. Okay, so let's do we did our electron count. All right, so let's continue with that. All right, so here we've already done it. It's platinum 4. Platinum 4 was D6, and then we had plus 8 for the 4 NH3s. We had plus 4 for the 2 Cls. We had an 18 electron complex, and we said that is going to be a stable complex. All right, so now I want to know more. So I know that I have 4 coordination number here, 2 coordination number here. So I know my coordination number is equal to 6, so I know I am octahedral. Now I want to know if I have strong field or weak field ligands. All right, so nitrogen, NH3, when you have nitrogen ligands, those are strong field ligands. If I have CLs, I have weak field ligands. So now you have both strong field and weak field. So you have to remember that as long as you have at least one strong field ligand, you are going to be low spin. All right, so you have low spin. They don't all have to be strong field to be low spin. One or more strong field is low spin. To be a high spin, you have to have all of them be weak field ligands. All right, so it is low spin. And so now we can put in our orbitals. And we can put in our D6. And so since it is low spin, all of these 6 electrons spin down at the bottom. All right, and so it is diamagnetic, which means, of course, 0 unpaired electrons. And now the hybridization. Since these two are empty, the hybridization is a D2sp3. All right, so let's do the next one. So part B. All right, so here we have NH3, which is a 2-0, but we have 2 of them. So this is going to be a 4 electron 0 for those 2 ligands. The chlorine is a 2 minus 1, so it's a 4 minus 2 for the 2 chloral ligands. All right, and so the platinum has to be plus 2. All right, so for part B over here, we have platinum 2, and that is D8. All right, plus we have 4, plus we have 4, we have 16 electrons. All right, remember, we will say that anytime we get 18 or 16, the chances of those being stable are in the 90+%. All right, so those are more than likely stable. Most all of them that are 16 or 18 are stable complexes. All right, so now we have a coordination number equal to 4 because we have 2 NH3s, we have 2 CLs. So our coordination number is equal to 4. All right, so it's either going to be square planar or tetrahedral. Remember, if your coordination number is 4 and you are D8, which it says right here, you are square planar. So if your coordination number is 4 and you are D8, you are square planar. And so now you have your electrons to put in. And I don't care if you put it like the book has it or if you put it this way, it doesn't matter. All that matters is when you put in your 8 electrons that everything has a pair. All right, so again, diamagnetic, 0 unpaired electrons. The hybridization, again, with square planar, the top is always empty and it never changes. The hybridization for square planar is always dsp2. It takes that d orbital, then an s, and then 2 p's for its 4 orbitals. All right, and then of course NH3 is a strong field ligand and Cl2 is a weak field ligand, but that doesn't make any difference. It's square planar, it's low spin. So if they were all chlorines, it wouldn't make any difference. It's square planar, it's low spin every time. Doesn't matter that it has strong field ligands. It's always a low spin. All right, part C. Part C is a platinum Cl6 minus 2 because we have our 2 K pluses. So this is minus 2. All right, so we have our 6 CLs. Each CL is a 2 electron minus 1. So this is 12 electrons total and minus 6 total. In order to get a minus 2 overall, we have to have a platinum that is a plus 4. All right, and so we have platinum 4. On the periodic table, the number above platinum is 10. So platinum 4 is D6. plus the 12 electrons from the ligands. We have an 18 electron complex. This is a stable platinum complex. All right, and so now we look at our ligands. They are all chlorines. Chlorine is a weak field ligand. So chlorine, weak field. It is the only ligand. 6 chlorines. All right, and so it's going to be a high spin. And so we have our 3 on the bottom, our 2 on the top, and we have our high spin with our D6. So 1, 2, 3, 4, 5, and 6. We have 4 unpaired electrons. So that is a paramagnetic. All right, and so those are occupied, those 2 on top. So the hybridization is sp3d2. All right, and then there's another one here that is a little tricky. I want to run through that one. Go back to that one, but I want to do the tricky one first. Nope. Okay. There it is. All right, so here, so this one will trip you up because you're going to look and say, I have a coordination number of 2, I have a coordination number of 2, and you would say your coordination number is 4. And that is right, well, every time except for this one. Coordination number is not 4. All right, you have to know what En is. En is ethylene diamine, which is NH2, CH2, CH2, and NH2. All right, and so it is coordinated on this side and on this side to the metal. So 1 En is 2 coordinations. And so you have 4 coordinations for your 2 ENs. Each one has 2 coordinations. You have 2 of them, 4 plus the 2 CLs. So this has a coordination number equal to 6. It looks like 4. It is not 4. Ethylene diamine, each one has a coordination of 2. And so your coordination number is 6, and this is octahedral. All right, and then your ethylene diamine, those are neutral, and that is a 4 electron neutral. So each En is 4 electrons and neutral. And then your Cl, each Cl is 2 electron and -1. All right, and so this is -2, this is 0, this has to be a +3. So your cobalt has to be a cobalt 3 in order for that to give an overall charge of +1. All right, so you go to your periodic table, you find cobalt. And cobalt is in a column with a number 9 on top. So I know that cobalt 0 would be D9. So cobalt 3 is D6. All right, and then I have my 4 electrons from my 2 chlorines, and I have my 8 electrons from my 2 ethylene diamines. And so I have my 18 electron complex, which is a stable complex. All right, so you have your D electrons, you have your ligand electrons, and then you have your total electrons. If your total electrons are 16 or 18, those are almost always stable complexes. You would always predict them to be stable. All right, so now we know we have our ligands. We have Cl ligands. Cl, these are weak field. But En is ethylene diamine. It is attached through nitrogen. These are strong field. And as long as you have one or more strong field ligand, you are going to be a low spin octahedral. So octahedral can be high or low. It depends on the ligands. If you have a strong field ligand, low spin. If they are all weak field ligands, then it's going to be high spin. All right, so then when we put in our 6d electrons in our 5d orbitals here, The 60 electrons are all going at a low spin, and so you have diamagnetic, 0 unpaired electrons. And the hybridization, since those two orbitals are empty, it is a D2sp3. And so you can write these as cis and trans as well. So you can have your trans with the chlorines, or you can have your cis with the chlorines. We're not going to do enantiomers with octahedral. All right. Note that we have the name. They give the name. It is a dichloro, right? Chlorine's negative. That's why it ends in O. Remember, ethylene diamine. The name ethylene diamine contains the Greek prefix. When your name contains the Greek prefix and you want more than one of them, then you have to use the naming of bis, tris, tetrakis, pentakis. And so since there are 2 ethylene diamines, you don't say diethylene diamine, you say bis ethylene diamine in the name. All right, let's go back here and do this one right here. Yeah. All right, so here we're back to our platinum. I feel like we already did that one. Yeah, we did do this one. All right, so remember your platinum. This is platinum 2. Platinum 2 is D8. The coordination number was equal to 4. Again, that's square planar. Now, when you are square planar, then you can have geometric isomers. So square planar, you can have cis and you can have trans. So when you have your square planar, that's tetrahedral. If you have your square planar, you can have your chlorines that are 90 degrees away, which is cis, or you could have your chlorines 180 degrees away, which is trans. So you can have cis and trans for square planar. You can have cis and trans for octahedral. You cannot have cis and trans for tetrahedral. When you are tetrahedral, then the only way to get stereoisomers is if you had all of these be different. If this was A, B, and then C, and then D, if they were all 4 different, then you would take the mirror image and it would not be superimposable. All right, so if you have a chiral tetrahedron, then you have enantiomers. Which means the mirror image is not superimposable. All right, so for your square planar, you can't have enantiomers. You're just going to have cis and trans isomers for your tetrahedral, just like in your carbon compounds. Your L and your D, you have right hand and left hand if you have 4 different ligands. All right, let's do a homoprobe. All right, let's do this one. All right, so this is just give the structure. Right by the naming. All right, so we're going to do a diaqua. So the name is right there for you, diaqua. Then dicyano. And then copper 2. All right, so diaqua, that's right there. That means you have 2 waters. So you're going to have H2O sub 2. Dicyano, you're going to have CN sub 2. And then you have a copper. All right, so you would have a copper complex. And the copper is +2. All right, and so that's a 0, that's a -2, so that is a diaqua dicyano-copper 2. That is a neutral complex. Now, my question is, what's the coordination number? Well, the coordination number is 2 waters, 2 cyanides, so the coordination number is 4. All right, and so now we know it's either going to be square planar or it's going to be tetrahedral. So we find copper. You go to your periodic table, copper's number 29. You look at the number above copper, it is 11. And so a copper 0 would never exist because if you ever write D11, it's going to be counted wrong because D can have a maximum of 10. All right, you never put a D more than 10. The maximum number for D is 10. So a copper 2, though, is D9. So I'm not going to say copper 0 is D11, but I'm going to know that the number on top of the copper is 11. But I know to never write down D11. All right, so copper 2 is D9. All right, that is not D8. So this is tetrahedral. The only way you're going to predict square planar with your coordination number of 4 is if you have a D8. All right, so now the total electrons, you got your D9 plus your 4 from your water plus your 4 from your cyanide. You have a 17 electron complex. You would not predict that to be a stable complex, but it is. This is a stable copper complex. Again, we're only going to predict stable for 18 and 16, but again, other electron numbers are stable. It's just 16 and 18, like all of them are stable almost. All right, the next one to name is potassium hexachloroplatinate 4. Potassium hexachloroplatinate 4. All right, so it says platinum 8 because potassium is the cation, and this is part of the anion, and that's why it is a platinum 8. All right, hexachloro, that means you have Cl6. You got a platinum, and it is a complex where the platinum is +4. Your chlorines are all -1, so that's -6. That means you have to have 2 potassiums, because that would give you a +2 and a +4, which is +6 -6. There's your neutral complex. All right, and so we already did this one. Your coordination number is 6. It's octahedral. These are weak field ligands. That means it's going to be high spin. And platinum 4 is D8. D6, sorry, D6. Platinum 4 is D6. Platinum 4 is D6. Plus the 12, you have an 18 electron complex. Again, we already ran through this one. And since it is high spin, that means you're going to put your electrons up high. For your tetrahedral, we didn't put the electrons in. So the tetrahedral, remember, is 2 and then 3. So this is our D9 tetrahedral, high spin. All right, so your tetrahedral, always 1 in each before you pair every time. So down here for your D9 tetrahedral, that is your electron that you put in for your 5 orbitals. And we will continue doing homework for the rest of the week.